Welcome students, a pleasant good day to everyone. Now in this class we will learn how to integrate this particular integral negative infinity to infinity ln of x to the power of 4 positive 1 over x squared positive 1 times dx. I will be using the technique given by Leibniz to solve this question. So foremost, what I wish to do is, clearly you can see that the numerator and the denominator, both of them are even functions, and because of that I would be utilizing the all-important integral property. Suppose you got integral a to b f of x times dx. In this case a is negative infinity and b is positive infinity. So let me rewrite it in this fashion: negative infinity to positive infinity f of x dx. Now if f of x is even, then I can rewrite this as 2 times integral 0 to infinity f of x times dx. So using this property I would be rewriting this to be as 2 times integral 0 to infinity ln of x to the power of 4 positive 1 over x squared positive 1 times dx. Now what I wish to do is, I would like to somehow rewrite x to the power of 4 positive 1. Now let me rewrite this as x raised to the power of 2 positive. Now you got you got 1 there. Now I would like to know what other ways I can rewrite 1 as. Now from complex numbers we know that I squared is equal to negative 1. Now is it possible for me to include 2 i's in such a way that when I multiply I will be able to get the quantity x to the power of 4 positive 1. So I'm going to rewrite this in this following fashion. So let me first place the 1 there. This is, I want to write it as a product of 2 quantities. Of course, if I were to have a I here and a I here, I multiplied with I should give me positive 1. So that would only be possible if I have a negative here and a positive sign here. So clearly I into I would give me I squared, but since there is a negative sign I need to place a negative sign, and that negative sign would impact the outcome and change it to positive 1. So I have almost got what I want, but since the degree has to be x to the power of 4, I need to place a x squared here and x squared here. So what am I doing here? I'm rewriting this as a positive b times a negative b. This is actually equal to a squared negative b squared. That's exactly what I'm doing. So in this case, if you were to multiply these two, you would get x squared raised to the power of 2 negative I squared, right? Now this is going to be x to the power of 4. I squared is negative 1. So this in turn would give me x to the power of 4 positive 1. This is important. We need to split x to the power of 4 positive 1 in this fashion. Otherwise it would be very difficult for us to actually integrate. So this is equal to, this numerator is rewritten as ln of x squared positive I times x squared negative I divided by x to the power of 2 positive 1 times dx. Now ln of a times b is equal to ln a plus ln b. So I can use that logarithmic property to rewrite this as ln of x squared positive I positive ln of x squared negative I. So you got a denominator for this, and then we need to have the operator dx. So what I wish to do in the next step, I would actually rewrite this as 2 integrals. So this is equal to 2 times integral 0 to infinity ln of x squared positive I divided by x squared positive 1 times the dx positive integral 0 to infinity ln of x squared negative I times dx divided by x squared positive 1. Now I'm going to define a function to handle these 2 integrals. So let me just take some, this is the Leibniz technique, right? This is how the integration is actually solved. So let us define this function. let us define a new function. Now you need to bear in mind that new function should be able to span both the quantities. So I'm going to take I of u is equal to integral 0 to infinity. Now let me just take this as ln of x squared positive u divided by x squared positive 1 times dx. So this is my I of u. Now we need to get the values, or in other words, for u is equal to positive I, we'll get the first integral, and for u is equal to negative I, we'll get the second integral. So the entire function that we have just utilized here will be able to get our values, get our integrals when u is equal to I. So this will be the case when u is equal to I, you will get integral 0 to infinity ln of x squared positive I times dx divided by x squared positive 1. This is first case. When u is equal to negative I, you would get I of negative I integral 0 to infinity ln of x squared negative I divided by x squared positive 1 times dx, right? So therefore this, if I were to take this as 2, what is this 2? Therefore 2 can be rewritten as this is equal to 2 times of what? I of I when u is equal to I added with I of when u is equal to negative I. So this is what we have to obtain, and we will substitute the values over here and simplify and obtain the result. That is our objective. So this is going to be our objective. Now what I wish to do is I would like to actually get some boundary values. Now why am I trying to get them by boundary values? Because when we integrate, we will encounter the constant c, and we need to obtain the value of the constant c. That is very important, right? So without the boundary condition, it's not possible for us to obtain. So let us go back to the original definition of our function. So I of u is equal to integral 0 to infinity. So we have ln of x squared positive u over x squared positive 1 times dx. So when u is equal to 0, suppose I take u is equal to 0, I get I of 0 is equal to integral 0 to infinity ln of x squared divided by x squared positive 1 times dx. This is what I've got. Now the question is, we need to obtain the integral value. What exactly is this? Let us take x to be equal to some 1 over t. So if I were to take x is equal to 1 over t, therefore dx is equal to negative 1 over t squared times dt, right? So ln of x squared is going to be, x squared is 1 over t squared. I can rewrite this as t raised to the power of negative 2, and then I will make the substitution there. So if I were to do that integral, when x is equal to 0, t is equal to infinity. When x is equal to infinity, t is equal to 0. Now you have ln of x squared, so I need to substitute the x squared. X squared is 1 over t squared, so I can rewrite this as t raised to the power of negative 2, right? So that's always possible. So let me just write that down. Ln of 1 over t squared, I'm going to write it as t raised to the power of negative 2 divided by x is 1 over t, that's going to be 1 positive, this is going to be t squared divided by t squared times dx is negative 1 over t squared times dt. Now this is what we've got, right? So t squared can be cancelled. Now what I wish to do is, I've got ln t raised to the power of negative 2. Now I would like to just retain 2 there, but push the negative sign down. So what I'm trying to say is, if I were to have something like this, ln a raised to the power of b, then I can rewrite this as b times ln a. I can very well do that. But in this case, what I wish to do is, I would just like to extract this negative sign. This negative 2 is nothing but negative 1 into 2, right? So let me just keep the 2 there and move the negative 1 down. So this can be rewritten as negative ln of t raised to the power of 2. This is perfectly possible. And in the denominator, I got 1 positive t squared. Already you got a negative sign here, so it's going to be negative dt, and the limits are infinity to 0. Negative negative will become positive, so it's going to be infinity to 0 ln of t squared divided by 1 positive t squared times dt. Now I want to change the limits. If I were to change the limits, this is going to be negative of 0 to infinity ln of t squared divided by 1 positive t squared times dt. Now I can actually replace the variables to x. No harm would be done. So this is equal to negative 0 to infinity ln of x squared divided by 1 positive x squared times dx. So all the variables are replaced with x. But what is exactly this? What is exactly this? This is nothing but I of 0. This is what we have started, and this is what we've been gravitating. So this is equal to negative I of 0. But what do we have on the left hand side? On the left hand side we started with I of 0, right? So what exactly this means? Pushing this to the other side, this would mean 2 times I of 0 is equal to 0. Therefore I of 0 is equal to 0. So this is the boundary condition that we have obtained, and we will be utilizing this condition. So this is important. Now let's jump back to the system that we started with. I of u to be as integral 0 to infinity ln of x squared positive u divided by x squared positive 1 times dx. Now what I wish to do is I would like to differentiate this. Now if I differentiate this, I would get I dash of u. Now this differentiation that is happening here would be taking place with reference to u. So it's going to be d over du of integral 0 to infinity ln of x squared positive u divided by x squared positive 1 times dx. Now if you were to change the order, you need to ensure that this is convergent. Now clearly this entire quantity that we see here is convergent. Because of the fact that this is convergent, we can shift the differential operator and the integral operator. So that would mean we got 0 to infinity. Now when we are placing d over du, we wouldn't be able to place it as d over du because of the fact that there are two variables involved, u and x. So I would be placing it as dou over dou u of ln of x squared positive u divided by x squared positive 1 times dx, right? So now I need to actually, so this is actually in this fashion. So dx is outside the parenthesis. So I need to differentiate this with reference to u. Now this is constant because there isn't any u there. So you can safely take that constant out, 1 over x squared positive 1. And now you need to differentiate ln of x squared positive u. So u is the variable here. So when you differentiate ln of x squared positive u, you get 1 over x squared positive u times differentiation of x squared is 0, differentiation of u will give you 1. So that is for d over du, or in other words I should say dou over dou u. So this is multiplied with the dx, and there is an integration from 0 to infinity. So this is what we have got. Now what I wish to do is I would like to use partial fractions to resolve what? Resolve 1 over x squared positive 1 times 1 over x squared positive u. Now clearly you can see that in the denominator you got only a quadratic quantities. So there isn't any combination of linear quantity. Because of that fact, I can break this quantity 1 over x squared positive 1 times x squared positive u as a over x squared positive 1 positive b over x squared positive u. So upon cross multiplying, you get a times x squared positive u positive b times x squared positive 1. On the left you get 1. Now if I were to take x squared is equal to 0, let x squared be equal to 0, in other words let x be equal to 0, so I would get u times a positive b is equal to 1. That would be one value. The next value, if I were to take x is equal to negative 1. So what happens when x is equal to negative 1? X is equal to negative 1. So a positive u times a 2 times b. I can replace, so on the left it's going to be 1. So this is equation, say this is equation 1, this is equation 2, or I'll take it as a and b. Right. So from here, so this means u times a is equal to 1 negative b. So wherever I get ua, I can substitute 1 negative b. In fact, instead of taking it as for ua, I will say take it for b. So I will just take b is equal to 1 negative u times a. I can substitute that value. So it's going to be a positive u times a positive 2 times of 1 negative u times a is equal to 1. So this is equal to a positive u times a positive 2 negative 2 times ua. I can add these two, so that would give me a negative u times a, and then I have a positive 2 there, positive 2, and there is a 1 here, so I can push the positive 2 to the other side. So it's going to be 1 negative 2. A can be taken out. I get 1 minus u. This is a negative 1 is equal to a times of 1 negative u. This is what I have got. Therefore, I can write a to be as negative 1 over 1 negative u. Now, I can actually flip this quantity, negative 1 over negative of u negative 1. So, this would mean a is equal to 1 over u negative 1. So, I got a value for a. Take the value for a and substitute it here in b. Actually, 1 negative ua, so 1 negative u times a. So, this is equal to 1 negative of u of 1 over u minus 1. This is what we've got. You cross multiply u minus 1 minus u divided by u minus 1. Negative u positive gets cancelled, giving you negative 1 over u minus 1. So I'll just retain this as 1 over u minus 1. So this is my value of b. So therefore b is equal to, let me put that, b is equal to negative 1 over u minus 1. So now we can take these values and we can actually substitute them over here. So we can substitute them over here. So this is equal to, my a value is 1 over u minus 1 times x squared plus 1. This is one quantity, followed by my b value is negative 1 over u minus 1 times x squared positive u, right? So we need to now integrate this. My page has run out. I need to go to the next page. So this is the partial fraction split that we have got. Now we are expected to integrate dx over x squared positive 1 times x squared positive u. This is nothing but integrating this entire quantity. 1 over u negative 1 times x squared positive 1 followed by 1 over u negative 1 times x squared positive u times dx. Limits are 0 to infinity. U minus 1, you can take it out. So it's going to be 1 over u negative 1, integral 0 to infinity. Now I want to distribute dx. So it's going to be dx over x squared positive 1 negative integral 0 to infinity dx over x squared positive u. Now this is tan inverse of x, so this is 1 over u negative 1 tan inverse of x. The limits are 0 to infinity, so place that, followed by, I can rewrite this u to be as root of u squared, right? So let me show that to you. This is going to be written as root of u squared. If I were to do that, this is going to be 1 over a tan inverse of x over a. So this is what I've got. So the limits are 0 to infinity and we need to apply the limits. So if I were to apply the limits, tan infinity is pi over 2, tan inverse of infinity is pi over 2, and tan inverse of 0 is going to be 0, right? Followed by 1 over root of u, tan inverse of infinity in this case is pi over 2, followed by 0. So if you had to rewrite this is going to be 1 over u negative 1 pi over 2 negative 1 over root of u times pi over 2. So pi over 2 can be taken out, so you get pi over 2 times 1 over u negative 1, right, times, you already taken pi over 2 out, so you got 1 over root of u. Now this is equal to pi over 2 1 over u negative 1. If I were to take the LCM, this is going to be root of u negative 1 divided by root of u. Now can I write u negative 1 as root of u negative 1 times root of u positive 1? Is it okay for me to write it? Because this is going to be a negative b times a positive b, giving me a square negative b square, which is nothing but u negative 1. So utilizing that over there, this is pi over 2 1 over root of u negative 1 times root of u positive 1 times root of u negative 1 divided by root of u. right? So root of u negative 1, root of u negative 1 goes away, giving you pi over 2 times you have 1 over root of u times root of u plus 1. So this is what you've got. On the left hand side you got I dash of u, right? So now you need to get I of u. So for that we need to integrate both the sides. So upon integrating both sides, what do we get? Upon integrating both sides. So what exactly happens when you integrate I dash of u? This would get us back the function I of u. Now in this case we need to integrate. So this is going to be integral of, I have to write this as, let me write this as root of u times root of u positive 1 times, we have to integrate it with reference to du. So you got pi over 2 there and you got a 1 there. So this is what we need to integrate. Now what I wish to do is, I would like to take, let u be equal to, I need to remove the square root, right? So I'm going to say u to be equal to sine square theta. So du is equal to 2 times sine theta times cos theta times d theta. This is for du. Now what happens when you place sine there? So let us just check. We need to do some simplification in the process. So I want to write root of u positive 1. That is going to be root of sine squared theta positive 1. Now root of sine squared theta is going to be sine theta. That's going to be sine theta positive 1. This is what I get for root of u positive 1. And then again I have root of u. So root of u would give me, therefore root of u is going to give me sine theta there. So let me just directly substitute and see. So pi over 2 integral, my du is 2 times sine theta cos theta d theta divided by my u is sine theta. My root of u plus 1 is going to be sine theta plus 1. So clearly I get a 2 being cancelled out, and my sine theta gets cancelled out. I have a cos theta. So I have a cos theta divided by 1 positive sine theta and d theta. Now if I were to take another substitution, let 1 positive sine theta be equal to some t, and differential of sine theta is cos theta d theta. So this is equal to dt. So if we were to substitute it here, so cos theta d theta is going to be dt, 1 plus sine theta is t. So this is going to be pi times ln t. So I'm using ln t, so I will have to place a modulus there. Ln of modulus t, which is equal to pi times ln of t is 1 positive sine theta plus c. Okay, so I have just placed t is equal to 1 plus sine theta. Now I want to retrace it back. I want to go back, right? This is fine, but I want to get the original function u variable, right? So that is imperative. So from here I need to replace what is sine theta. So from here sine theta is nothing but root of u. That is important for us, because without that we wouldn't be able to find the value of c. So this is going to be pi times ln modulus of 1 positive root of u positive c. This is modulus. You need to place the mod sign. So this is what we have got, right? But we need to get the value of c. Getting the value of c is important. Now what is on the left hand side? The left hand side is I of u. So this is I of u is equal to this entire thing. Now take u to be equal to 0. Let u is equal to 0. What do you get? You get I of 0 is equal to pi times root of 0 is 0, ln of 1 modulus, this is ln of modulus 1. That's nothing but ln of 1. 1 is a real value, so that's going to be 0 there. So that would mean you have a 0 there plus c, so c is equal to 0. That is the reason we found out I of 0. I hope you are able to catch it. So c is lost, c is already annihilated. So I of u will be equal to pi times ln of modulus of 1 positive root of u, right? So I need to go to the next page. So let me write that down. I of u is found to be as pi times ln of modulus of 1 positive root of u. This is what we have got. Now we need to extract two values. That is important, right? That is when u is equal to I and u is equal to minus I. So these two values have to be obtained. That would give us the final value. That means we need to add them up, and of course there are a few simplifications that have to be done. So let me just take when u is equal to I. So I of I is equal to pi times ln of modulus of 1 positive root of I, and when u is equal to negative I, this is equal to I of negative I is equal to pi times ln of 1 positive root of negative I. Now if I were to take this as some 4 and 5 or some 5 and 6, just to be on the safe side, I need to add 5 with 6. Okay, adding 5 with 6. So therefore I of I plus I of negative I is equal to pi times ln modulus of 1 positive root of I positive pi times ln modulus 1 positive root of negative I. Right, this is what I've got. So now we need to add these two quantities. So that would be pi times. Now ln A plus ln B. Now let me write that. Ln A plus ln B is equal to ln of AB. Using that property I can rewrite this as pi times ln modulus 1 positive root of I times 1 positive root of negative I. Okay, this is what I've got. Now we know equivalence representation for I. So we know that I is equal to e raised to the power of pi over 2. This is the representation we have got. Now root of I is nothing but I raised to the power of 1 over 2, which is nothing but e raised to the power of I times pi over 2. This is entire thing raised to the power of 1 over 2. Right, this is because I raised to the power of 1 over 2. So what is that? That is nothing but e raised to the power of I times pi over 4. So this is for root of I. Now you have to know that I as a representation for negative I also, right? So let me show that to you. Negative I is nothing but 1 over I. Now you might be wondering how is this possible. So let me show that. Now 1 over I is there. I multiply by I divide by I get I over I squared, which is nothing but I over negative 1, which is equal to negative I. So that's the reason 1 over I can be rewritten as negative I. So have that in mind. So because of this fact, I can actually rewrite negative I to be I raised to the power of negative 1, but I has got a representation e raised to the power of I pi over 2. This has to be raised to the power of negative 1. So this is equal to e raised to the power of negative I pi over 2. Right. So this is my negative I. So I am going to substitute all of this over here. So this is equal to pi times ln modulus of 1 positive root of I is e raised to the power of I times pi over 4, and followed by modulus 1 root of negative I. This is going to be, this has got a square root, right? This is minus I. So let me find out what is root of negative I. Root of negative I is negative I raised to the power of 1 over 2. That's nothing but e raised to the power of negative I pi over 2 raised to the power of 1 over 2. That would give me e raised to the power of negative I pi over 4, right? So that is the value there. So e raised to the power of negative I pi over 4. Now Euler has given us a formula. E raised to the power I theta is equal to cos theta positive I times sin theta. So e raised to the power of I pi over 4 is nothing but cos pi over 4 positive I times sin pi over 4. Cos pi over 4 1 over root 2, and this is I 1 over root 2. This is for I pi over 4. Also for e raised to the power of negative I pi over 4, this is going to be negative I theta. So cos is an even function. The only problem we will have is, or I should say the only difference is negative I over root 2. So this is the value. So take these two values and substitute it here. So that would give me pi times ln modulus 1 positive 1 over root 2 real part followed by imaginary part I over root 2 modulus 1 positive root 2 negative I times root 2. Now this is mod z1 into mod z2. Now there is a formula, mod z1 times mod z2 can be rewritten as mod of z1 z2, right? So because of that, this is equal to pi times ln modulus. So when you multiply, this is going to be 1 positive 1 over root 2 squared negative I squared, that's going to be positive, it's going to be 1 over 2. So if you expand this, this is going to be pi times ln modulus 1 positive 1 over 2 followed by 2 times root of 2 positive 1 over 2. 1, these two can be added, right? So that will become 1 plus 1. So that's going to be pi times ln modulus 2 positive 2 can be written as, let me show you, 2 is nothing but root 2 times root 2. So root 2 can be cancelled, you have a root 2. So this is the value you have got. But the original question wants you to find what is required. We have to find 2 times of I of positive I of negative I. This is what is required because of the symmetry, or I should say because we changed integral negative infinity to infinity to 2 times integral 0 to infinity. So there is a presence of the 2 that has to be catered. So we need this. Let me write this. We need this. So therefore this is equal to 2 times pi of ln, no, mod of a real quantity. You can drop the modulus. So 2 positive. Now you can drop the modulus. You cannot drop the modulus before, right? So this is the place that you can drop because these two components are real. You are getting a real value here, right? So this is where you need to drop. So have that in mind. So this is 2 positive root of 2. Now a times ln b is ln of b over a. Push this 2 to the other side. So it's going to be pi times ln of 2 positive root of 2 squared. So because of lack of space, I need to move to another page. So this is what we've got. So now what we need to do is we need to expand this. So I would be utilizing a positive b whole squared formula, which is a squared positive b squared plus 2ab. So utilizing this, I would get 4 positive 2 times of root 2 positive root 2 squared, that's going to be 2. So this is going to be pi times ln of 4 added with 2 positive 2 times 2 is 4 times the root 2. Now this is going to be pi times the ln of 6 positive 4 times root 2. So this is what we've got. But we can utilize the same thing. We know that a times ln b is equal to ln of b raised to the power of a. If we were to utilize that, this is going to be ln of 6 positive 4 times the root of 2 raised to the power of pi. What is this? This is the required solution for this question. Thank you everybody. Enjoy your night.